Hello, it's Dr. Daystorms, and this discussion here is the beginning of Chapter 9 in our book. And we've gone over some of this in class, so part of this is to reinforce the topics that we've covered thus far, and then we're also going to take it up a notch and go into a little greater detail. So today we're talking about the molecular geometry, and the reason why this is so important is because the structure yields the function, and that's true for whether we're talking about a chemical compound or anything. The way that something is built or it's constructed is what will help dictate its functionality. So in particular, we want to focus on the molecular shape and why it's important. We're going to discuss electron domains and then really talk about geometry. Okay, we're going to start off with electron geometry and then focus on the molecular geometry. They're very similar, but there's a slight difference, a slight nuance. It's a different. Okay, so the shape of a molecule plays really important roles in its reactivity, and so we just have different ways of putting molecules together, and we're going to talk about these different shapes and hopefully correlate what you've done in lab with what we've done in lecture thus far. And that there's only so many ways that you can put molecules together. Okay? It's very important to keep in mind the total number of atoms that's coming together in the molecule, the total number of bonding pairs versus non-bonding electrons. So if you make this note, make note of the number, that is, of bonding and non-bonding electron pairs, you can actually predict the shape of a molecule with quite a degree of accuracy. So, how can we do this? Let's just look at an example. This is ammonia, NH3, and all you have to do is just look at the total number of what's called electron domains. Okay, because you want to maximize the distance between electrons. Since electrons are all negatively charged, they're going to repel each other, and so they're going in 3 dimensions. In 3 dimensions, they're going to want to maximize their distance away from each other. Okay, so in this instance here with ammonia, we have 1, 2, 3 bonding sets of electrons. And then we have 1 non-bonding pair. So that means that there's a total of 4 regions of electron density. Okay, so we call these electron domains. So if we assume that you place these electron pairs or these electron domains as far as possible, you can predict the shape of this molecule. So let's look at this generic region, or generic form. Okay, so every pair of electrons is considered to be an electron domain. That being said, though, it should be noted that a double bond is considered, or a triple bond for that matter, a single electron domain. So if we look at this around the central atom of A, we have that double bond is 1 electron domain. There's a second electron domain, a third electron domain, and then the fourth being the lone pair of electrons. Okay, so since double bonds and triple bonds share their electrons between 2 atoms on the same side, or the same face, they just count as a single electron domain. I want to reiterate that. Okay, this whole idea of maximizing the distance in 3 dimensions is called the VSEPR. Some people call it VSEPR model. Okay, so the VSEPR model stands for valence shell. But remember, the valence shell is the outermost electrons. So it's the valence shell electron pair repulsion theory. VSEPR or VSEPR model. And so here, this is for the molecule CCl4, carbon tetrachloride. We have carbon being the center atom, and it's making 4 bonds to 4 different chlorides. So it kind of looks like the electron density kind of looks like a pyramid, the way that's shown up here. Okay, and so what the V. Sepper theory states is that the best way to arrange these electron domains in space is one that minimizes the repulsions among them. So you want to maximize the distance by minimizing the repulsions, okay? So here we have really the four chlorines are like the edges of this triangle. Okay, and by the way, this shape is called tetrahedral. And so there are only a set number of electron domains that are possible. Now notice these are electron domains, so they include both the bonding electrons and the non-bonding pairs. We've already in class discussed the fact that we could have four be tetrahedral, and a perfect tetrahedral would have an angle between any of the atoms, or between any of the electron domains of 109.5. It sounds like a great radio station. 109.5. Okay? Whereas you can have three when there's two electron domains, and it could be between three different atoms. The two electron domains is linear, which is 180 degrees. Three will be trigonal planar, because they're all in the same plane, and it's going to be 120 degrees. We've already talked about four being tetrahedral. 5 is called trigonal pyramidal. And it's like two pyramids, two of the three-sided pyramids on top of each other, inverted on top of each other. And notice that there's one set that goes straight up and down. Those are called the axial. And then there's three that are in the same plane, and those are called the equatorial positions. Then we have octahedral for 6. Okay, octahedral has 90 degrees between every domain, and then the trigonal pyramidal depends. There's 120 degrees between the three that are in the triangle part, and then there's 90 degrees between the axial and equatorial positions. So let's do an example together. The very first thing that you need to do is draw the Lewis structure. Okay, so let's do an example of CO2, which is carbon dioxide. So we draw the Lewis structure for it. And we're going to be looking at the central atom, right around this carbon here. So after we've drawn that, let's determine the number of electron domains. So we have one electron domain here, and the second electron domain there. So there's two electron domains, and so that means that this is a linear electron domain geometry. And we can even further state the fact that the angle from here to here is 180 degrees. Okay? So let's work another example. Let's look at ammonia. Our good friend ammonia. You first need to draw the Lewis diagram, which would look like this. Okay? Now, let's count the number of electron domains that there are. We have 1, 2, 3, 4. So since there are 4 electron domains, that means that the electron domain structure is tetrahedral. Okay? So you would expect that to have an angle of 109.5 degrees between any two of the hydrogens and between that and the lone pair electrons. That's called the electron domain structure, but that is not the molecular domain structure. When we want to look at molecular domain structure, what we do instead is you don't include lone pair electrons. because this is what the molecular structure really looks like. In reality, you've got this lone pair of electrons taking up a lot of space, so it looks much more squatty. And so it's not tetrahedral. In fact, we're going to find out that this one is called trigonal pyramidal. So it looks like a little pyramid. There's a much better picture coming up. Okay, so for an electron domain structure, or electron domain geometry, you're looking at all the electron domains. For a molecular structure or molecular geometry, you do not include lone pair electrons. So let's look at this example in a prettier sense than what I can draw. Okay, so for the electron domain geometries, you draw the Lewis structure, and you can see here that it's a tetrahedral for electron domain geometry. However, that is not the case. Okay, this geometry corresponds to the number of electron domains, but it's not necessarily the case for the molecular geometry. And so I like this picture much better because it clearly shows how you take the formula, you develop a Lewis structure, you can look at the electron domain geometry, which is tetrahedral, but then you don't include the lone pair electrons because this is what the actual molecule looks like. And it's called trigonal pyramidal. Okay, because it's trigonal, because the base has three different, 1, 2, 3, so 3 different legs on the base. And it makes a little pyramid, so it's trigonal pyramidal. Okay, so the molecular geometry is defined by the positions of only the atoms and molecules, not the lone pair electrons, the non-bonding pairs of electrons. And that's very important to note. Okay, so within each electron domain, there might be more than one molecular geometry. So what does that mean? Here we're going to look at what if there are 4 electron domains. And I like this picture here because it shows the different possibilities. If all 4 electron domains are due to bonds, like in methane, CH4, then it really is tetrahedral. However, if we have a set of lone pair electrons, it's not. It's trigonal pyramidal. If we have 2 sets of lone pair electrons, it's called bent, which is like water. So I like to draw water out this way. It's a little easier to see. That's bent. So now we're just going to work through the different possibilities here. So, if there are only 2 electron domains, then that means that the example that we've already done was carbon dioxide. There's only one molecular geometry that's linear. There's only one way to put those and to maximize their space, and that's linear. Note if there's only 2 atoms in the molecule is going to be linear no matter what the electron domain is, because you only have two points of reference, and the shortest distance between 2 points is a line. Okay. Now, if there are 3 electron domains, then you can actually have 2 different possibilities. One possibility is our good friend trigonal planar. So BF3 is an example of that. The angle between these 2 fluorines right here is going to be 120 degrees. The other possibility is like in nitrite anion, and that's a bent, and that's where we have 3 electron domains. However, one of them consists of lone pair electrons. Now if we look at comparing non-bonding electrons and bonding electrons, what you're going to find out is that the non-bonding electrons take up much more space. Okay? And I kind of like to think of this as sort of the idea of like a 2-parent household. So if this would be a bonding, say, between a carbon and a hydrogen, for example. And so the electron density between the 2 nuclei, the nuclei are positively charged. The electron density is attracted to this, and so it's kept in check. It's only in a certain limited space. However, if you have a nucleus that's got lone pair electrons, there's not that second nucleus there to help keep it on a tight leash. And so what's going to happen is it's going to balloon out and try to minimize its own repulsion with itself. So because of this, the non-bonding electrons are going to push down on the bonding electrons. So that's why if you look at the examples here with ammonia and water and you compare that to methane, methane does have that perfect tetrahedral 109.5 degrees. However, ammonia, it's a little less than 109.5, it's at 107. Water is even less than that, it's at 104.5. And the angle here between the lone pair electrons and the hydrogen is going to be greater than 109.5, especially between these two. The reason being is they just take up more space. They're fatter than if they were in a bond. Lone pair electrons is going to cause the other bonds to be smaller than what you would expect. The bonding angle to be smaller than what you'd expect. Okay. Alright. Another thing is double bonds, which is very similar in that sense, because a double bond has a lot of electron density. And so you would expect in this instance, this is a trigonal planar, and so you would think that between the carbon and whatever's here, I'm just going to put X's, you would expect it to be 120 degrees in a perfect world. Oh, it's not wanting to come up. 120 degrees in a perfect world. Reality is going to be a little less than 120 degrees. So down here it's going to be a little less than 120 because the lone pair, because the double bonded electrons have more density to them, and so they're going to push down on the two single bonded electrons. They're in those bonds right there, the single bonds. And so it's going to make that one a little less than 120, and it's going to make this angle here, whoops, this angle here, it's going to be just a little greater than 120. And same thing here, this angle is going to be a little greater than 120. Oops, I did the wrong direction. 120. Okay. Alright, so now when there are 4 electron domains, then we have 3 possibilities, and we've actually already discussed these 3 possibilities. One possibility is tetrahedral. If they are all 4 in bonds, it's tetrahedral and the angle is going to be 109.5. If you have one set of lone pair electrons that are non-bonding and 3 bonds, like ammonia, it's going to be called trigonal pyramidal, and it's a little less than 109.5 between those hydrogens in that sense. If you have 2 sets of lone pair electrons, the angle, it's called bent, and for the molecular geometry, and the angle between the 2 hydrogens is even less than what you would expect if there were 3 hydrogens. I don't expect you to memorize the number, but to understand the trend, the only number that I want you to memorize for tetrahedral is 109.5. But I want you to realize that, use logic, that anytime that we have lone pair electrons, the angle down here is going to be less than 109.5 because they're being cramped or crowded due to those lone pair electrons. Okay, now whenever we have 5 electron domains, then there are 2 distinct positions. That's axial, which goes to the up and the down, and then there's equatorial. Equatorial means there are 3 in the same plane, so they're 120 degrees apart from each other, and the axial to equatorial is 90 degrees. Okay, and then the only one here really that I want you to pay attention to at this point in time at least is if you have 6 and they all are for bonding, it's called octahedral. Okay, and the angle between octahedrals is 90 degrees. Okay, there are 3 possible shapes, which is that there's square pyramidal, and then there's also square planar. And we'll actually, you may cover square planar later in Gen Chem 2 whenever we talk about some of the metal bonding shapes. So the shapes and angles that you need to know, and just make sure that you can understand what happens whenever there's lone pair electrons, is linear, bent, trigonal planar, which has the ideal angle of 120, trigonal pyramidal, tetrahedral, which has the ideal angle of 109.5, trigonal bipyramidal, octagonal, and then once again qualitatively know what effects lone electrons and double bonds have on the shape of the molecule. Hopefully this has helped explain this really important topic here, talking about molecular shapes or geometries. I'll see you in class.